All right, guys, we're going to do another quick proof, add something to our knowledge, and also just be exposed to more of these proofs and what they look like, how they work. So what do we know right now is we know that the derivative of x to the n is n times x to the n minus 1, as long as n is an integer. We proved it for positive integers, and then we proved it for negative integers. And spoiler alert, I've told you this before, eventually we're going to know that it's true for all numbers. It doesn't matter. But what we're going to do today is we're going to prove that it's true for a rational power. So what is a rational power? Well, let's let n equal to an integer divided by another integer. So p and q are integers, with the only qualification that q can't, for obvious reasons, be equal to 0. So if I'm looking at the function f of x equals x to the n, that's the same as the function x to the p over q. What's an over? Didn't write that right. And that's the same as the qth root of x to the p. So what we've got here is that y is equal to the qth root of x over p. And I'm going to get rid of that rational symbol by taking both sides to the qth power. So this implies that y to the power of q is equal to x to the power of p. And the reason we've waited till now to prove this is because we needed implicit differentiation. So let's take the derivative. I'm going to go to the next page just to give myself lots and lots of room. Y to the q equals x to the p. So I'm going to take the derivative of both sides. So the derivative of y to the q, since q is an integer, is q times y to the q minus 1 times the derivative of y with respect to x, and the derivative of x to the p is p times x to the p minus 1, since p is an integer, and we'd already proved that it worked for integers. So let's see, what are we going to do? Well, first off, I'm going to divide both sides by q, and I'm going to divide both sides by y to the q minus 1. So we now know that the derivative of y with respect to x equals p over q times x to the p minus 1 over y to the q minus 1. Don't be confused by the fact that I separated the fractions. I divided by q and divided by y to the q minus 1. So what do we got next? Well, what do we know about y to the q minus 1? Well, y to the q minus 1 is x to the p to the q minus 1, agreed? It's because of that. And that means that y to the q minus 1 equals x to the, and we're going to multiply this. I'm not happy with this. Wait, what did I do wrong here? What did I do wrong? I did something wrong. Oh, wait. That's p over q. Sorry. So back up just a second there. I overgeneralized here. We know that y is equal to x to the p over q. So that y to the q is irrelevant. So multiplying these together, I get y to the q minus 1 equals x to the p over q times q minus p over q. These q's cancel or reduce, depending on how you want to say it, and I get x to the p minus p over q. So that's y to the q minus 1, which is right here. So let's do a little quick substitution. The derivative is p over q times x to the p minus 1 divided by x to the p minus p over q. And of course, we can just subtract these powers, since that's a shortcut we have. And so this equals P over Q times X to the P minus 1 minus P minus P over Q. P minus P is 0. Negative and a negative is a positive, and what I get is that the derivative of y with respect to x is equal to P over Q times x to the, well, the P over Q becomes positive, and the 1 becomes negative. And this was given that y is equal to x to the P over Q. So there's what we've got. We started with y equals x to the P over Q, and we proved that we can just bring the P over Q out front and then subtract 1 for the new power, which is exactly what the power rule had said. And since n was equal to P over Q, it would be fair to then just take this and say, well, that this is x to the n becomes, the derivative is n times x to the n minus 1, given where we started, which is that n is equal to P over Q. All right, I'm going to stop that video right there. It was just a quick proof for you. And thanks for watching.